There is such a thing as a polyprotic acid. Most of the acids that we study are monoprotic acids. They will only release one hydrogen ion. So they will have, they have within them only one that is likely to get away. Monoprotic because it's a proton that's getting away. A polyprotic would have two or more. So, and we have additional names. Instead of just saying polyprotic, we can specifically say how many. A diprotic would give out two possible. Here you go. Sulfuric acid is an example of a diprotic acid. You can have a triprotic acid. You can have these go up way more than this if you have some of these organic ones. But as far as physical chemistry is concerned, triprotic is as high as we get. Here are 3 in phosphoric acid that could possibly come off and exist in the equilibrium. So you know, polyprotic, monoprotic, diprotic, triprotic. Uh-oh, there's a star. Okay, interesting. Let's look at this. It says, what's the pH of a 0.2 molar solution of sulfuric acid? Gosh, guess what? The first one just plain comes off. The second one has a Ka that isn't huge. It's not like 10 to the 5th or 10 to the 6th. Oh, so this pH, I'm going to have to do some work on this. I can assume that since that is a strong acid, that the first one comes completely off. The second one, not so much. So for this, I am going to say that at first, what happens, one-way trip, because it's a strong acid, we're going to form ammonium ions, and we're going to form hydrogen sulfate ions. That's a one-way trip. So whatever this was, 0.2 molar for us, that's going to become 0.2 molar. So each is 0.200 molar to begin with. But what's really going on has to do with this second one. I'm going to have to keep this and keep going because the second ionization is going to form additional hydronium ions. So the reaction that we're really interested in is when this one continues to fall apart a little more, because that's the second acid ionization for this. So the second one comes off. HSO4 with some more water is going to form an equilibrium because, you know, it's not like a million, right? It is going to then have lost the other hydrogen, so it's going to form sulfate ions and more hydronium. What's initial? Well, initial is after this first one has happened, after this has happened. So these are each going to be the 0.200, 0.200. That's just liquid water, so it doesn't count. This is separating them out. And I'm saying initially there's none of this. What's the change? Well, that can't stay as none, right? And it can only go up. So if it's going up, the only way it can go up is if this is falling apart. When this falls apart, it'll make one of each of these. So this is also going to be a plus X. And at equilibrium, 0.200 minus X, X, and X. Whoop, that's not just X. Where's that? Don't forget about it. Oh my goodness, you gotta watch yourself. This one was fine, but this one, okay, don't do that. You'll be unhappy if you forget that one. But these were set because the first ionization was completely to the right. So you could just take the original concentration of sulfuric acid and say now that each of these was the 0.200 molar. And then you use reasoning to figure out how the change goes. Anytime you have a zero, you know it's not going to stay there. And you can come up with this. Okay, what do we get then for our Ka2? Okay, Ka2, we have it set at 0.012, but it's going to be these, the products. So X times X plus 0.200 over this guy, 0.200 minus X. When I get done with that, I'll have X squared plus 0.212X minus 2.4 times 10 to the negative third equals 0. There's my quadratic formula. Oh, quadratic equation. My quadratic formula is going to be X equals minus 0.212. Oh, since that's a minus, I don't have to worry. I can just use the positive square root of the 0.212 squared minus 4AC. Oh, there's another minus. Isn't that nice? So plus 4 times this, all under there, and then over the 2a, so it's just over 2. And you're going to get 0.011. Okay, so that's the X. The hydronium concentration is given by, oh, it was supposed to be an equal sign. X plus 0.200. So we're going to get 0.211 molar from that. And now we feel like we've done enough work that we should be done, but we're not, because that doesn't answer the question. The question was, what's the pH? All right, that's okay. We got one more step and we'll be done. pH minus the log of the hydronium ion concentration. So minus the log of the 0.211, which is going to give us 0.65. And you might ask yourself, do I really have 3 sig figs? If so, you can just sort of say to yourself, well, what if I had said it was minus the log of 0.21? If I did that, I'd get 0.68. So you see, it's a very close. It only differs in the last sig fig, so I'm not feeling badly about this. And this is just, what did we do? It's a strong acid. So the first one completely dissociates. We started our rice table with the second dissociation. And the first dissociation helped us form the initial conditions, the I part of our rice table.